Okay, so let's do another one. Let's look at a car. We've got our little car. I'm not a good drawer. Okay, so here's our car, and we're just tooting right along, going this direction. And after a little bit, we come to a stop and apparently lose mass. Okay, so this is the same size. Pretend it's the same size. All right, so we have our car. We've also left the road. Let's just say we're still on the road. I don't draw well. But anyway, we have our car, and we are moving along, and we are traveling at some velocity. We don't know what it is, and we come to a stop. Now, what is going to cause it to come to a stop? Okay, so we want to think about that a little bit, because that's going to define our system. What we want to look at is we have our car. What are the forces acting on the car here? Okay, we've got Earth. We've got Earth pulling it down. We've got the normal pushing it up. But since we are still on the ground, we don't have any change in height. We aren't leaving the Earth. We're not going down into the Earth. So really the Earth doesn't affect our motion. There's a force acting on it, but it doesn't change the energy of our system. The gravitational potential energy here is the same as the gravitational potential energy here. It doesn't change. So we can ignore that in this particular problem. So we don't need to put Earth. But what is acting on it? We've got friction, right? Where's that friction coming from? In order for our car to stop, we have to have some friction acting against our car. So let's just say the road. Okay, the road's over here, and there's this force of friction acting on the car. And it's acting in that opposite direction of motion. And so we've hit the brakes. We don't have our motor pushing on us that way. We just have the friction acting in the opposite direction so that we stop. So our system over here is our car and the road. We're going to draw our little graph. All right, we've got kinetic energy. Okay, we're moving. We decided that we don't have any gravitational potential energy. We don't have any spring potential energy. So those two we don't have. So all of our energy is wrapped up in that kinetic energy because of its motion. So let's just draw our boxes. So we have 5 boxes of energy that we have. Okay, now again, this doesn't really give us an exact quantity. It's just a way to represent it. Now what happens to that energy? Over here now, let's do our little bar graph. What happens to our car? We've got our kinetic energy, but we don't have that anymore. We didn't gain any gravitational potential energy. It didn't go up. There's still no spring, okay? But what happened? Friction, right? So friction was acting on this car. So that energy was dissipated as heat. So this is where all of our energy goes. We start out moving. The road has a force of friction over some distance, remember, that acts to dissipate that energy and stop the car. Now here we have, for our conservation equation, we have our kinetic energy then is equal to the energy that was lost due to friction. Equation-wise, we can write that out as 1/2 mv squared as our equation for kinetic energy. Now this is that force of friction, right? So this is the force of friction over some distance. So we would have to find the force of friction in order to determine that quantity. And we would have to know how far we're going in that situation. Now what I want you to look at, what if we do not include our road? What if our system is only the car? We can do this again with only the car. So over here, we've got our kinetic energy again. Okay, so same thing. Whoa, I'm getting fatter. All right, so we have our kinetic energy over here because our car is moving. Now, here's the thing. If the road is not a part of our system, what is the road doing? Because we've lost that kinetic energy. But since we don't have the road as our system, we can't say that that energy is still a part of our system. So if the road is not a part of our system, this energy isn't a part of our system anymore. So let's sketch this for a second and see what this looks like. Okay, we've stopped. We don't have any kinetic energy. We didn't change height. We don't have any, there's no spring. Okay, now this can't be a part of our graph because it's not a part of our system. So is energy conserved here? What happened here? Well, we did work, right? So since the road is outside of our system, what we have is the road doing work on our car. So we're going to draw a little arrow with 5 boxes, 2, 3, 4, I think that's 5. This arrow is going to go out. We're doing work here. So there is work being done on the car. It's a negative work because it's taking energy out of the system. So this arrow going this way means that energy is leaving the system. So when we write this conservation equation then, what we're going to have is we're going to have our kinetic energy is equal to the work done on the car by the road. Now what does it look like if we take this equation out? Well, it looks the same, right? Because what is work? Work is force acting over a distance. So when the road does work on the car, it applies this friction force over some distance. This is the same thing. It's just in this case we're going to define it differently because our road was not a part of our system. So this is where defining that system becomes really important. So being able to talk about what are the forces acting on whatever it is we're talking about. Okay, the car is what we're concerned with. What's actually acting on it? Okay, and are we going to include it in our system? Those are those big questions.